So we've got a concave mirror, which we're assuming is a portion of a spherical shell. We're not really going to worry about the rest of the sphere. We're only looking at this portion of it. But that sphere does have a center somewhere. So this would be the center of that sphere. And where should we expect the focal point of this mirror to be?
And closer to the mirror in front of the center.
Yeah, it should be exactly halfway between the center and the surface. So this will be the focal point. And then this distance would be the focal length, f. And we're assuming that this is the side of the mirror that light is traveling on. The other side, this is presumably maybe we've got like a wall here. And this whole side is dark. We've just got a wall with a bulged inwards mirror surface. All the light is happening on this side. And let's say we have an object that is, let's say, out here. So this is our actual physical object. And we're assuming light is being emitted from the object. And maybe the object's actually emitting light, maybe it's a candle flame or something, or maybe we've got light from something else that hits the object and bounces off. But either way, we can treat the object as the source of these beams of light. Light is coming out of the object in all directions, and we can focus on just the top of the object and assume everything else will follow the same pattern. So light's coming out of the top of the object in all directions, but we don't need to keep track of all those rays of light. We just need to look at the ones that are going to be easiest to draw. And for this concave mirror, or really for any mirror, concave or convex, what would you expect to be the easiest rays of light to draw in? Of all these directions, what would be a direction for a ray of light that's going to be easiest to analyze?
The one that goes horizontal first?
Yeah, we could have a ray of light going horizontally. And generally, I wouldn't say horizontally because it doesn't have to be horizontal. The important thing is that it's parallel to the optical axis itself. But if you had the mirror arranged in a different alignment, it's not going to be horizontal, but it's important to be parallel to the central axis, the optical axis. So we have a ray that starts off going parallel. That ray is going to hit the mirror and bounce off. And we could draw in the normal line and measure the angles and make sure everything matches up. But the whole point of setting up the ray tracing like this is that if a ray starts parallel, it's going to hit the mirror and bounce off in what specific way?
Diagonally?
Diagonally, and specifically through which point?
Focal point?
Focal.
Any ray that starts off parallel to the central axis is guaranteed to bounce off toward, well, either towards or away from, but through the same line as the focal point. So that's one of the important properties of a spherical mirror. The whole point of defining the focal point is the one point that any parallel ray, any ray that starts parallel, is going to bounce off through the focal point. So if you just have a curved mirror like this, if you send in a ray parallel to the axis, it's going to bounce off. Send in another ray parallel to the axis, it's going to bounce off. Send in another ray parallel to the axis, it's going to bounce off, and so on. All those rays that were originally parallel are going to bounce off in such a way that they all intersect at one point. We call that point the focal point. So any ray that starts off parallel is guaranteed to bounce off along the line through the focal point, because that's what the focal point means. It's the one point that every parallel ray hits when it bounces off. So that's one trajectory light could take. One of the rays of light from the object is going to happen to be parallel, and that'll bounce off through the focal point. What other ray of light could we draw out that's going to be comparatively easy to analyze, that's predictable?
Through the focal point?
Yeah, we could have another ray of light that's passing through the focal point itself. because of all the rays that come out of the object, one of them is going to happen to pass through the focal point. And this is another important property of the focal point. Any ray of light that's along the same line as the focal point is going to hit the mirror and bounce off in what sort of way?
Parallel to the optical axis.
Exactly. That ray of light hits the mirror and bounces off to become parallel. So you've got a ray of light that starts off parallel and bounces to become through the focus. A ray of light that starts off going through the focus and bounces off to become parallel. And those rays of light are going to be intersecting at one very specific point, specifically this point right here. So at that point, let's say you're standing over here and watching this situation. Your eyes receive rays of light traveling like this. If you don't know anything else at all about what's going on, your eyes just pick up these rays of light and your brain says, oh, I know light travels in straight lines. These rays of light must have come from this point. So you think you see something going on at that point. And what do we call that point?
The image?
Yeah, this would be the image. So your brain thinks, the object must be there. And of course, the object's not there, but it makes sense to think it's there because the rays of light seem to be coming from that point. So we would say this point is the image. Since the image is below the axis as opposed to the object which is above the axis, that means this is going to be an upside down image. So the image is upside down, or we would say inverted as compared to the original object. Also, would you consider this to be a real image or a virtual image?
Real.
Yeah, it's a real image, and why is that? Why would we describe this as real?
Because the rays intersect.
Yeah, if the rays actually pass through that point, we call that a real image. So image means any point that the final rays of light seem to be coming from. If they actually did pass through that point, we call it a real image. Any questions on that so far? So it looks like this mirror produces a real image of the object. The real image is a little bit closer to the mirror than the object is. The image distance, that is this distance here, is smaller than the object distance. So that suggests that the image is going to be a little bit smaller than the object, because the ratio of image height and object height should be the same proportions as the ratio of image distance to object distance. Can you repeat the real image part again? Yeah. Image just means a point that the light seems to be coming from. So ignoring everything else that happened before, if your eyes are just getting these beams of light, your brain thinks those beams of light must have come from this point. And so your brain thinks it sees something at this location, even though that's just an empty point in space. That's what an image means. The image is just this empty point in space that the final rays of light seem to be coming from. So that's the image. However, since these rays of light actually did pass through that point, we call it a real image, as opposed to a virtual image, which would be a point maybe somewhere back here. Like if the final rays of light don't intersect, but they're spreading out, they seem to be coming from some point way back here. That would be called a virtual image because the rays of light didn't actually pass through that point. And how do we know it's smaller? Ultimately, because it's closer to the mirror. The image is closer to the mirror than the object is. And in this case, it's pretty close they're pretty close to each other. I may have just not drawn this accurately since I'm just freehanding it. But it looks like the distance from the mirror to the image is a little bit smaller than the distance from the mirror to the object. That would suggest that the image size is a little bit smaller than the object size. And this goes back to the concept of magnification. Magnification factor, M, is defined as height of the image over height of the object. So if you actually measure the object height, that's HO, the height of the object. If you had some way of measuring how tall the image appears to be, that's hi, the height of the image. That ratio is m. So for instance, if m, the magnification factor is, let's say 3, m being 3 would mean the image is 3 times as big as the object. M being 1/2 means the image is half as big as the object. M being -1/2 means the image is half as big as the object and upside down. A negative value for M means the image is flipped over. So negative represents direction here in a sense. So this is the definition of magnification. It's the ratio of image height and object height. But that also happens to equal negative image distance over object distance. So I and O represent the distance from the mirror to the image and the distance from the mirror to the object. So this distance would be O, and this distance would be I. All these distances are going to be measured from the mirror itself. If the image is virtual, even if the image is virtual, being behind the mirror, we'd still be measuring the distance from mirror to the image. So the sign is not important. In terms of deciding whether the image is bigger or smaller, positive or negative sign doesn't matter. All that matters is how far is the image from the surface of the mirror versus how far is the object from the surface of the mirror. The direction, which side of the mirror the image is on, is going to make a difference in the sign. So that it will change whether the image is right side up or upside down, but it will not affect the size of the image. Any questions on that so far?
Casey, I have a quick question. So if the image is like closer to the mirror, will it always be smaller then?
Yeah, because if the image is closer to the mirror than the object is, then I is smaller than O. And we're looking at absolute value here, ignoring positive and negative sign for now. If the image is closer to the mirror than the object is, then I is smaller than O. So this fraction is less than 1, which means HI will be smaller than HO. The image height will be smaller than the object height.
Okay, and that goes the same way for like virtual images?
Yeah, regardless of what type of image it is. And this is ultimately about similar triangles. If you draw out a triangle of, so we've got object distance and object height, and we can draw this line as a hypotenuse. So there's a triangle. We could also draw another triangle with the image height and the image distance and this hypotenuse diagonal. And these diagonals actually form another path that light can travel. If you've got light from the object traveling towards the exact center of the mirror surface here, it's going to bounce off, forming the same angle with the normal line. So these angles are the same. These angles are both right angles. So these are similar triangles because the angles match up. Similar triangles means the proportions are the same. So the ratio of image height over object height has to match the ratio of image distance over object distance. So this equation really comes from the idea of similar triangles from geometry, that these two triangles have to have the same proportions, the same ratios. So that ultimately just boils down to the ratio of distances is the same as the ratio of heights, with a negative modifier to account for being upside down. Any other questions on that so far?
I have a question.
Mm-hmm.
You said that if the image is closer to the mirror than the object, then the image is negative, I is negative?
Image is smaller than the object.
Small.
Whether it's positive or negative is really more about which side of the mirror it's on. The general idea is whichever direction light is traveling at the end, like in this case, we've got light from the object going towards the mirror, hitting it and bouncing off. The final direction light is traveling is to the left. Direction of the final rays of light. So that is the direction the rays of light are traveling after they've interacted with the mirror. And this is also true for lenses. Whatever direction the rays of light are traveling after they've interacted with the lens or mirror, we call that the positive direction. So since the rays of light at the end of the project are traveling to the left, in this example, we would treat to the left as the positive direction. Is the image on that side of the mirror?
Yes.
So that means since the image is on the side of the mirror where the rays of light are traveling at the end, we would say this side is the positive side, so the image value, I, will be a positive value. So if the image is on that light side, that is the side of the mirror where the final rays of light are traveling, then the image distance, I, is positive. And that's always going to be true for what kind of image?
Real images.
Yeah. Any real image has to be on the side that light is actually traveling on. If it was on the dark side of the mirror, then it would be a virtual image. So any real image is going to have a positive value for I because it's on the side of the mirror that light is actually traveling on at the end. Whereas a virtual image would be on the dark side of the mirror. It's on the side that light is not traveling on at the end. So we'd call that the negative side or the negative direction. And in that case, the image value would be less than 0, a negative number. So that's what we would use in order for using the magnification equation or the lens and mirror equation. You choose a sign for I based on which side of the mirror it's on. So a real image is on the light side of the mirror, so that would always be a positive value for I. A virtual image would be on the dark side of the mirror, so that would always be a negative value for I. That doesn't mean you put a negative into the equation. It just means when you solve for I, you will find a negative value for it, or you should get a negative value. Same is true for the focal point. If the focal point is on the side of the mirror that light's traveling on at the end, which will be true for a concave mirror, then F is a positive value. On the other hand, if you have a convex mirror, if the mirror was shaped instead like this, and you've got light coming in from this side, the focal point still has to be halfway between surface and center. And that focus is on the dark side of the mirror. Light's traveling on this side, focus is on the opposite side. So we describe the focus as a negative value here. So this distance is still the focal length, but we treat it as a negative value for purposes of plugging it into the equation. So a convex mirror is going to have a negative value for F. And that's going to make the light spread out rather than coming back together. Any questions on that so far?
Really quickly, so when we solve these, do we have to use like absolute value signs, or can we just solve it with like positive and negative?
Including the signs in these. Don't use absolute value. Actually include any positive or negative signs that show up. Because
Okay.
the negative and positive values are going to behave very differently in these equations.
Yeah, I don't know, because in GL he was like, be careful of like the absolute values, or like use the absolute value sign sometimes, so I was a little confused.
If you're doing things like comparing sizes, like if you want to know, is the image bigger or smaller than the object? Going back to the magnification equation, when you calculate M, the magnification, positive or negative values for M are just telling you whether the image is right side up or upside down. So if you don't care about the orientation, whether it's right side up or inverted, if all you care about is the size of the image, then you should be looking at the absolute value of M. For instance, if M is -3, that means the image is 3 times as big as the object and upside down. If M is +3, then the image is 3 times as big as the object and right side up. But in both cases, the image is 3 times as big as the object.
Okay.
But generally, when you're working out these equations, I would keep very close track of the positive and negative signs because those make a big difference in the results.
Got it. Thank you.
Let's try one more ray tracing example while we've got this concave mirror here. I'm going to erase these rays and draw in a different object. So same concave mirror, same optical axis, same focal length, wherever that was. Yeah, something like that. And then if we need it, the center is just going to be twice that far out. But this time, let's put the object closer. Is the equation the same? Yeah, this equation works for concave mirrors and convex mirrors, and also concave lenses and convex lenses. Works for concave and convex lenses and mirrors. It's really convenient because you can just use this one equation for both types of mirrors and both types of lenses. No modifications needed. You just got to be very careful about how you keep track of the positive and negative signs. In general, focal length is going to be positive for any diverging mirror, converging mirror or lens. Like this concave mirror takes these rays of light that are coming in and bends them closer together. So any converging mirror or lens, you would treat the focal length as positive. If it's diverging though, like for a concave or convex mirror, you get these rays of light coming in, this is going to scatter them. The rays of light coming in parallel are going to get scattered. And we would call that a negative value for the focal length. So regardless of whether it's lenses or mirrors, if the optical apparatus makes the light converge, you would use a positive value for F. If the optical device makes the light diverge, spread out, you would use a negative value for F. But with that consistency, positive value for F if it's converging, negative value for F if it's diverging, you can use this same equation for both types of lenses and both types of mirrors. And that's really why we adopt the sign conventions we do. This is why we call some focal lengths positive and some focal lengths negative, so we can use the same equation for all of them without having to modify it. Any other questions on that so far? So let me put in an image here, or an object. Let's say we put an object at this location. Maybe 2/3 of the way to the focus. In fact, let's actually put in some numbers here. Let's say we happen to know that the focal length of this mirror is 6 centimeters. And let's say we put the object at a distance of 4 centimeters as measured from the surface, because we always measure these from the surface. So F is 6 centimeters, O is 4 centimeters. And let's try this both ways. Let's use geometry and ray tracing to figure out approximately where we can expect the image to be. And then let's also use algebra with the ray tracing, the thin lens equation or thin mirror equation to predict mathematically where it should be. First of all, the ray tracing. We got rays of light coming out of the object in all directions. But what direction do we want to start with? What would be a direction that's easy to predict? If we have a ray of light from the top of the object traveling which way?
Parallel to the optic axis.
Yeah.
And
So it starts off parallel to the optic axis.
and it reflects into the focal point.
Yeah, that's going to bounce off, reflect directly toward and through the focal point. By the way, if it was on a diverging mirror, you'd have a ray that starts off parallel. It can't go towards the focal point because that would be passing through the mirror and it's got to bounce off. Instead, it bounces off along a line through the focal point. So that's how a parallel ray would behave if it was a diverging mirror. So either way, whether it's converging or diverging, any ray that starts off parallel to the axis ends up going along a line that also includes the focal point, even if the ray doesn't actually go through the focal point. It's still on a line that includes the focal point. So there's one ray. What's another ray we can draw here? Can we have a ray that goes from the object towards the focal point?
You can go up from the object and up to the mirror.
Right, because a ray from the object towards the focal point won't actually hit the mirror. But the important thing is being on the same line as the focal point. So if you draw a line between the object and the focal point, it doesn't really matter whether the ray itself passes through the focal point. Any ray that's along this line, so from the object, essentially going directly away from the focal point, even though it doesn't actually pass through the focal point, this ray straight away from the focal point is still collinear with the focal point. It's still on the same line. So that counts, and that's going to bounce off to become parallel to the axis. And there's also one other ray we can draw in. It's not really necessary, but sometimes it's useful. If you've just got two rays, that should be enough to establish an intersection. But one more ray that you can draw in, if you have a ray that's passing either through the center or directly away from the center of this, not the center of the mirror, but the center of the circle. One of the important facts about circles is that any radius, any line through the center, has to hit the surface of the circle at what angle?
90°.
Right, that's going to be a 90-degree angle, right angle. And any ray of light that hits the surface at a 90-degree angle is just going to bounce straight back. So any ray of light going through the center or directly away from the center is going to hit the mirror and bounce straight back along the direction it came. So that's a third principal ray you can draw in. Again, it's not strictly necessary. Two rays are enough to establish an intersection, but it can still be useful to have a third ray to make sure. In fact, there's really even a fourth ray you can draw in, although we don't usually do it. If you draw a ray from the object towards the center of the surface, like where the optical axis intersects, at that point, the normal line is the optical axis. So this should bounce off, forming the same angle with the optical axis. Again, not necessary. We really only need two rays, but drawing in more rays can sometimes be useful. If the ray passes through the center, yeah, any ray of light that either originates from the center or passes through the center, or even if it's just traveling straight away from the center of the, not the center of the mirror, but the center of that sphere, is going to form a radius with respect to that circle. Any radius is guaranteed to hit the circle surface at a right angle, so it's going to bounce straight back. So yeah, generally any ray of light from the center going outwards is going to hit the mirror and bounce straight back towards the center. And that's also true from a ray coming in from outside. If it's a convex mirror, if you're looking at the other side, where it bulges out, any ray of light coming in towards the center is going to bounce straight back out along the same path. That's one of the important properties of the radial direction of a circle. So we now have several final outgoing rays. We've got this ray of light, this ray of light, this ray of light, this ray of light. Are these rays of light going to intersect on this side?
No.
No, they're diverging. Even though this is a converging mirror, these rays of light are spreading out so much that even the converging mirror doesn't make them converge. And note that at the beginning, they were spreading out quite a lot. Now they're not spreading out as much, but they are still spreading out. They're never going to meet over here. But that doesn't mean there's no image. If you're standing over here observing these rays of light, your brain picks up these rays of light spreading out and thinks, ah, those rays of light must have come from some point back here. And this is where the idea of backtracing comes in. Even though these rays of light never intersect over here, we can say, well, they seem to be coming from some point further back. If you just backtrace along these in straight lines, all these points, all these rays of light seem to be coming from some point back here. So what would we call that point that they all seem to be coming from?
The image?
Yeah, This still counts as an image because it's where the final rays of light seem to have come from. Did the rays of light actually pass through that point?
No.
No, which is why we had to backtrace. If the rays of light really passed through that point, we wouldn't have had to backtrace. So what kind of image is this?
Virtual.
Yeah, this is a virtual image. It still counts as an image because it's still where the final rays of light seem to be coming from. But it counts as a virtual image because the rays of light didn't actually all pass through that point. However, since it's above the axis, just like the object was above the axis, it is a right side up image. So the virtual image is right side up. And note that it's behind the mirror instead of in front of the mirror. You're going to see what looks like this, and it looks like larger copy of the object on the far side of the mirror. And then I, the image distance, would be this value. Also, would you consider I to be a positive or negative value?
Negative because the image is behind the mirror.
Yeah. Since the image is on the behind side of the mirror, the dark side of the mirror, we would treat this as a negative value. And again, this goes back to the standard that the direction light's traveling at the end is the direction we call the positive direction. Since the image is on the other side of the mirror, the side that light's not traveling on at the end, we call this the negative side. And that convention is going to hold for lenses as well. Whether you're talking about mirrors or lenses, positive is the direction light's traveling at the end. Negative is the opposite direction to that. So if the image is on the side that light is traveling at the end, we treat I as a positive value. If the image is on the side where light is not traveling at the end, then I is going to be a negative value. And it looks like the image distance is larger than the object distance, that is, as measured from the surface of the mirror. So that means the image is larger than the object. And again, we could draw in those triangles. This triangle and this triangle should be similar triangles if we've drawn it right. And so they'll have the same proportions. Any other questions on the geometry of the ray tracing so far?
So if the object is closer to the mirror, that means the image would be behind the mirror and larger?
Yes, as long as the object, specifically if the object is closer to the mirror than the focal point. The focal point is really the break-even point here. If the object is further away from the mirror than the focal point, you get a real image. If the object is closer to the mirror than the focal point, then you get a virtual image. And that should be true for any concave mirror. For convex mirrors, it's going to be different. In fact, the convex mirror is only going to be able to produce a virtual image. So convex mirror, bulging out, only produces virtual images. The concave mirror can produce real or virtual depending on which side of the focal point the object is. Also, in fact, if you put the object on the focal point, let's say we've got our focal point here, and let's say the object happens to be on the focal point. If you try drawing out the principal rays here, you got a ray that starts parallel and bounces through the focal point. You've got a ray of light, well, through the focal point doesn't really work because it'll never hit the mirror. But if you have a ray from the center that bounces straight back, those rays of light are never going to meet. In fact, you could even draw a ray from the object towards the center of the surface, bounces off at the same angle. These rays are actually parallel. They never meet on this side, and they never meet if you backtrace. So if the object is exactly on the focal point, you get no image at all. Which means there's really three possibilities for a concave mirror. Object beyond the focal point means you get a real image. Object inside the focal point means you get a virtual image. Object exactly on the focal point means no image at all. So those are all the three possibilities. For concave mirrors, I can be positive or negative. For a convex mirror, you only ever get a virtual image. So the I will always be a negative value. And we can actually see this in the mirror equation here as well. If we write out the information we have First of all, we know F and O. We're trying to solve for I. We want to know where is that image exactly. Because we can see approximately where it is based on the ray tracing diagram. But if we want more accuracy, we need the actual numbers. So if we have 1 over O plus 1 over I equals 1 over F, and we want to find the value of I, how would you solve this equation for I? How could we algebraically isolate I in this equation?
You would do 1 over F minus 1 over O.
Yeah, we could subtract the 1 over O from both sides. And then what?
Then you invert.
If we invert, we get 1 over I becomes I over 1. Inverting this side, we get 1 over this whole thing. So we could leave it like this, but it's going to be kind of inconvenient to do so because we'd have to subtract 1 over 6 minus 1 over 4, calculate that, and then invert that again. But an easier way to do this is if we combine these into one fraction first. How would you combine 1 over F minus 1 over O into just one fraction? How would you get a common denominator here so we can combine those?
Multiply
is-
them by O and F.
Yeah, this one has an F in the denominator, but it's missing an O. So let's multiply by O in the numerator and denominator to keep it the same value. This one's got an O, but it's missing an F. So let's multiply F into the numerator and denominator, keeping it the same value, but just changing the way we're writing it. So that gives us 1 over I equals O over O times F minus F over O times F. Same denominator, so we keep the denominator and subtract the numerators, O minus F. And now we can invert both sides much more easily because we just have 1 big fraction equals 1 big fraction. Invert both sides, we get I equals, invert that, O times F over O minus F. So this is a much more useful rewrite of the formula. By solving it preemptively for I, we now have a formula for where the image is, and all we need to do is plug in these O and F values. So I find this version, the 1 over O plus 1 over I equals 1 over F, this is usually easier to remember, I think. But if you're going to have to solve for I several times anyway, go through the steps algebraically to put it in I equals whatever format. And then you can just plug in values of O and F whenever you need to. So let's try that. We plug in these values, O times F, that'll be 4 centimeters times 6 centimeters. O minus F would be 4 centimeters minus 6 centimeters. And what's 4 minus 6?
-2.
So negative 2 centimeters. And then 4 times 6 is going to give us 24 centimeters squared. But when we divide, one of the centimeters cancels out. And what do we get?
-12 centimeters.
So that would tell us that the image is, first of all, it's on the dark side of the mirror. It's a virtual image because of the negative. And it should be 12 centimeters away from the mirror. So it looks like I didn't really draw this to scale very well. The image should actually be 12 centimeters away. The object was 4 centimeters away. So we should expect the image to be 3 times as far away from the mirror on the other side, if I had drawn this really accurately. And going back to the magnification equation, if the image is 3 times as big as the object, 12 over 4 would be 3. So M would be 3. That is, the image is 3 times as big as the object. This even applies to the negatives. If you plug in -12 over +4, you get -3. But this negative brings it around to positive again. So the magnification is +3, meaning the image is 3 times as big as the object and upright. The positive means it's the same orientation. There's no flip to upside down. Any questions on that so far? And we can get other interesting results from this version of the formula, even if we don't have specific numbers. Like we found earlier that if you put the object on the focal point, you get no image. We can actually see that in this equation. If the object is at the focal point, then O equals F. If you just replace O with F, O times F becomes F times F. O minus F becomes F minus F. When you try to calculate this, what's going to go wrong?
It would be undefined.
Right. If you actually simplify, F times F becomes F squared, but F minus F becomes 0, and F squared divided by 0 is undefined. So because of that division by 0, that means we get no image at all. The algebraic difficulty here of division by 0, or the algebraic impossibility, I should say, means that we get no image. So that's algebraically why we get no image at all if the object is on the focal point. So you can find out all sorts of useful information about the possibilities involved here, like what happens if the object is further than the focal point, what happens if the object is closer than the focal point, what happens if the focal length is negative. Just by examining this equation and checking what happens if if the focus is positive or negative, what happens if O is larger than F or smaller than F. For example, let's say we're talking about a convex lens or convex mirror. For a convex mirror, F will be negative. What's O times a negative number going to be? And we generally assume O is going to be a positive number. If F is negative, though, in other words, if we've got a diverging mirror, which in this case would be convex in shape, we plug in a negative value for O, that's going to mean we've got a positive for O, positive for O, but a negative for F. What's positive times negative going to be?
Negative.
So the numerator is negative. And then for the denominator, we've got O, which is positive, minus F, which is negative. If you've got a positive and you're subtracting a negative, what do you get?
Positive.
Yeah, subtracting a negative is the same as adding a positive. So a positive plus a positive just becomes more positive. So overall for the image, we get a negative divided by a positive. That's going to be a negative result. Which means what kind of image?
Virtual.
Yeah, a virtual image. So we've just proven algebraically, without even using any numbers, just the idea of F being positive or negative and I resulting in a negative. If the focal length is negative, and of course the object is positive, then the image distance has to be negative, which we would interpret as if the mirror is a diverging mirror, then the image has to be a virtual image. So a diverging mirror can only produce virtual images. But a converging mirror can produce real or virtual depending on whether O minus F turns out to be a positive or negative number. That is, depending on whether O is larger or smaller than F. So you can figure out all that information algebraically by examining this equation and checking what sort of result do you get if F is positive, if F is negative, if the value of O is larger than F, or if the value of O is smaller than F, or if it equals F. Check those possibilities and check, does I become positive or negative as a result? So you can get a lot of information just by examining this equation and also comparing to the results of ray tracing for examples. So try messing around with ray tracing yourself, make up some examples, try putting the object further away, closer up, try maybe several different distances. Check the ray tracing as accurately as you can with a straight edge to get the line straight. And then also check the results in the thin lens equation to see what the exact values are. The more practice you get, the more intuitive this is going to become, because you're going to be able to, if you've seen lots of examples and worked them out yourself, it's going to be a lot easier to see a new example and think back, oh yeah, I remember doing an example like that where the object was in this place next to this mirror, and I remember that it behaved like whatever. So the more practice you get, the easier this is going to become. So keep at it. Any other questions before we go? All right, have a good weekend, keep practicing, and I will see you next time.
Thank you.
You're welcome.